Hello, everyone. This is astronomy. Oops, there I am. Hello, everyone. Now it's live. This is Astronomy 111X, Introduction to Solar Systems, and I am Frank. I'm the instructor for the course. I'm the guy in the videos. And we have office hours for 10,000 for about an hour or so today. Let's see, a bit about me, I guess. So I do astronomy and astrophysics. I particularly like things that go boom in the dark night sky. So I like explosions, I like supernovae, I like X-ray bursts, I like gamma ray bursts. And not just for the fireworks that they make, but also for the elements that they make. It's the stars that make the periodic table. It's stars that make the isotopes. And so ultimately, it's the stars that make all the carbon, the oxygen that make you and me. So we are stardust. And I find that just fascinating. And they come from stars. So that's what I do for research. I'm a theorist. So I appreciate the telescope. I enjoy observational data. But I don't particularly take the data myself. So I more calculate, I compute, pencil or paper to big iron computers. My presence is not too hard to find on the web. If you want to find out a little bit more about what I do, you can Google my name and I'm sure stuff will come up. Let's see. So today, what do we want to cover? I think the first thing I'll do is cover some of the questions that were asked on our discussion board, and I'll cover from there. I do encourage you to ask your questions on the discussion board, whether it's a conceptual question or whether it's a question on the quantitative aspects of the course, anything along those lines. Do post. I'm your best resource for that kind of stuff. So let's go ahead and answer a few questions, and then I will probably do a little presentation on time, how we got to time and where we are right now with time. And then we'll see where we're at, and I may go back to other questions, or we'll just see. Okay, so on the YouTube Live 1 session, let's see. Oh my goodness. Whoa. Okay. User Omwashin asked a whole lot of questions. Let's see. So let's just go through. So some of the astronomy questions. Why did Ophiuchus get the short straw when the Babylonians chose the zodiac signs? Probably because at the time, Ophiuchus had the smallest area on the sky, if you like, the smallest angular width, so that it would spend the shortest amount of time. The sun would spend the shortest amount of time in the constellation Ophiuchus, and so it was sort of like the runt got kicked out. So the one with the smallest amount, I think, is the one that got dropped to make it an even 12. And 12, of course, was a holy number. We're going to cover that a little bit when we get to time. It's why 12 is so prominent, 12 months in the year, 12 hours of daylight, 12 hours of night, AM, PM, mini-mart. So yeah, I believe that's why Ophiuchus got the short end of the straw, because it was the smallest. You mentioned the moon will keep slowly distancing itself from the Earth until I assume some equilibrium is established. Do we know if this will affect Earth's orbit around the sun? Yep, it reaches some equilibrium, and this is something we actually do in, I believe, the 3rd week of the course. The time scale for that is very long. on the order of about 50 billion years or so, until the Earth and Moon reach an equilibrium. And there'll be lots of other things happening in our solar system before it reaches equilibrium. For example, when the sun will begin its death phases, it will begin transitioning into a very large red giant star. And if it doesn't engulf the Earth and Moon, it will get darn close to it. And so there will be some dynamical effects going on. The Milky Way and Andromeda galaxy will be merging around that same time. So there'll be lots of things flying around. Somehow I'm a little dubious that it will reach its two-body equilibrium position before other bodies have an effect, or before other bodies have an effect, whether that's in our solar system, Sun, Jupiter, or whether it's other bodies coming in from the collision with Andromeda. Our local group consists mostly of dwarf galaxies. How does this compare to other galaxy groups? It's about the same. We're not atypical at all in that regard with regard to small galaxy groups. Obviously, larger galaxy groups are going to have more galaxies, so they'll have more dwarf galaxies. But if you look sort of at the distribution and take out the raw number, we're not horribly dissimilar from other small galaxy groups. Similarly, what percentage of observable galaxies are similar in size to the Milky Way or Andromeda? So the the dominant galaxy type is elliptical galaxies. And so why that is a great question. Could be the universe was just born that way. Could be that ellipticals are formed from spirals. That's a possibility. And so when you smash two spirals together, they make an elliptical galaxy. But large spirals in the observable cosmos, I believe the number, if I remember off the top of my head, is on the order of about 10%. Are these large fluffy spirals. Otherwise, you're usually a more numerous dwarf elliptical, or you're one of the large, most massive ellipticals. So, would precession of Earth's axis actually affect us in any ways, or just a thing that happens without consequence? Yes, affect us in any way. Yeah, it changes our clocks, for one, hugely. In fact, we're going to cover that. It's caused wars. It's caused mayhem at tax days. Yeah, we're going to cover that. So yeah, precession actually has a great deal to do with time and how we keep time and keep the clock synchronized. So that's another good reason to cover time today. Do you ever expect more constellation to be recognized where we stick with basically what we have, 88? I think they're kind of fixed, at least in the present epoch. If you wait long enough, of course, all those stars are actually moving. They're not actually fixed sticky dots on the sky. They do have some velocity relative to us. And so over time, the constellations will change. And along enough time scales, those constellations will in some sense begin to blur, begin to run into one another. And so at that point, let's say 100 million years in the future or so, you may want to redraw the boundaries or create new constellations or something, because once they start to diffuse into one another, it gets hard to distinguish what's what. So at that point, you may want to do a redistricting, if you like, of the sky into constellations. But the 88 we have are certainly going to be good for my lifetime, and almost certainly yours. So we're kind of stuck with those 88. Where have you been that's given the best view of the Milky Way without aid? The best place that I saw the Milky Way was in Hawaii. Got out on a near a beach. It was on a cliff. It was a new moon, so the moon wasn't out. And Hawaii has the advantage that there's not a whole lot of light around like there is in Phoenix. And you are out in the middle of the Pacific Ocean, so there's not other areas out there broadcasting lights. And so the sky is pretty dark there. And that was when I saw the Milky Way. I went, wow. Wow. To think that we used to see that every night is amazing. So yeah, that was the best place I saw it. Second best place I saw it was in Colorado. I was camping out there, and we were up around Mesa, Colorado. Also a new moon, and that was a pretty spectacular shot as well. So those are the two best places I've seen. How long will it be before total solar eclipses are a thing of the past? Okay, that's a good question. Don't know that number off the top of my head, but it's certainly calculable. So I'm going to punt on that one because I don't know that one off the top of my head. But it is an interesting. When will the last solar eclipse be? What's the date of the last total solar eclipse? Okay, I'll work on that. I'll probably post something on our discussion boards. Then we have really boring questions. It's about me. What made you want to study this field? Sounds like fun. Have you always wanted to do this? No. The first thing I ever wanted to be when I was in high school, I wanted to be a chemist. Because I had like a home chemistry kit. I thought that was cool. So I made aspirin. I did some bio stuff, taking lactic acid measurements of blood. So first I wanted to be a chemist, and it took me, I didn't decide I was going to become an astronomer and astrophysicist until I was into my 30s, let's put it that way. So I'd already worked in Silicon Valley and other sort of stuff. So I was sort of a late comer on to, in that respect, to astronomy, astrophysics. Do you teach on-campus classes in addition to the online ones? These days, nope. I teach strictly online. I'm more effective. I touch more students. I like it a lot. What's the best thing about your job? I get personal satisfaction out of it. I like it. I think it's a fun thing to do. Something about horse-sized ducks or duck-sized horses. I'm going to punt on that one. What are your thoughts on Elon Musk sending people to Mars? Besides that they will probably die quickly. Well, we're going to Mars. It's just a matter of time. Oftentimes our art leads our science. So you can think of the science fiction movies that we watch on television, or the movies, or the books, and they all have these phantasmic devices or amazing things we do. And so it sort of sets the target for us, and we go for it. Even our mobile devices, our Apple Watches, right? These all hark back to, in some sense, to our science fiction, to the early Dick Tracy movies, where he had this little gizmo on his wrist and it did everything for him. It was amazing. And so we're there. So we're going. It's just a matter of time, whether it's Elon or person after Elon. We're going. I'd like to see it. I don't know if I want to go, but I'd love to see it. Does your immediate community even care about this plans? Why or why not? Well, sure. It's humanity. Going to Mars has been on the target for a long, long time. Do you travel too much? Or do you get to travel too much? I guess to answer the question. Too much. Yeah, there is a bit of travel for what I do and where I am at in my trajectory. Various responsibilities to my collaborators, to my colleagues, and then in large to the community. So one of the things I do is I am an editor for one of the premier astronomy and astrophysics journals. So people write their research papers, they submit those research papers. It goes through a peer review process on whether it's acceptable for publication or not. And so I help guide and modulate that review process. So in that sense, and these are international journals, so it's service to the international community. And I like that a lot too. What's the coolest place you've been inside or outside of the United States? Coolest place. Do you mean actual temperature? Alaska. Every place is fun. Every place is unique. They all have their pluses. They all have their minuses. I think they're all great. About this course, you recently answered a question about getting an equation sheet proctored for the exams. Do we also get to use a calculator? Short answer, yes, but very specific ones. And we will, I need to give that guidance, don't I? I will send that guidance today. That needs to be sent out. Actually, no, it's on the test sheet. So yeah, you can use a calculator, but it has to be a web app calculator or a very simple physical calculator. But you can read about that on the instructions for the exam, which are up now. Will the design project come with additional instructions, or is this really open-ended? It's really open-ended. Whatever turns your motor over. It can be art, it can be science, it can be a little bit of both. You should touch what the learning outcomes for the course are, whatever you do. So if you look in the syllabus, there's a listing of learning outcomes. You should attempt to touch one or more of those learning outcomes in your design project. But yeah, it's open-ended. It's your chance to express what you like about astronomy or what you got out of this course. So, will we get to see previous examples? No. What I have found is that when you show people previous examples, you just get a bunch of copycats. So everybody thinks that's the right way to do it or the only way to do it. And so if I show them a pair of socks that somebody darned an astronomy motif, all of a sudden a sizable fraction of the design projects are all darning socks. So no, that's not the point. I want you to be creative. I want you to be original. I want you to do your own thing. So I don't show previous examples. You're quite welcome to share your design project with your colleagues. Just post something on the web, post a link to it. If you're making a video or something, you can post images of certain sizes on the discussion board. So you're quite free to share your design project when we get there, and that's perfectly fine. But sharing stuff up front, no, that biases what people do. CB Kunin, this course is so hard math-wise for my brain. How will I succeed if I barely get correct answers on lab 1? Ask questions. Really, ask questions on the discussion board. As you can probably tell, I'm pretty prompt in replying. Hopefully the content of the response is good too. So yeah, I'm quite willing to help with that, but you do have to ask questions. If you're just going to say this is hard, I don't know how to, I can give you, there's some additional resources on the discussion board, but that just saying it's hard is not actionable. So if you run into a question that you find challenging, go ahead and cut and paste it into a thread on the discussion board, and we'll go from there. You should also look to see if somebody else has posted the same questions so that we don't run duplicate threads. When that happens, I will typically pick the one that is the most explicit about how far they've gotten, and I'll run that one and just refer all the other threads to that particular one, just so we avoid a tremendous amount of duplication. Yeah. So hang in there. Week 1 is a wake-up call for most. Week 2 is the hardest for most. So this week is the hardest for most. And then I would say generally, people find it gets a lot easier as the course goes on. So hang in there, ask questions. Ma Perry 9, hi, I just wanted to start off saying I'm really excited for this course. Hooray! I've always enjoyed the ideas of astronomy and I'm excited to explore it. Thumbs up. So really the one question I have is pertaining to angular width. No, I'm not too great at math. Ask questions on the discussion board, but I know enough to do most of this work. Exclamation, yay, except for the angular width. Oh. I kept drawing straws and researching, but I could never get the correct formula to calculate the angular width, and I believe it wasn't on the math sheet either. Thank you. So there's several threads on the discussion board. And I hope one of those sufficed. In particular, I took one where I drew a circle and the distance around the circle. And so really that one way to get that formula is the mantra, you know, the part is to the whole as the part is to the whole. And so if you set up that proportionality, the part to the whole, one part being angles, so the angle that you're going versus the total angle, which is 360 degrees on a circle, versus the distance versus the radius, so it's the other part to the whole, and equating those two parts to the whole will give you the formula. There are other ways to get it, but that is the most geometric, the most intuitive on how to get it. And it is very definitely on our all the math sheet, absolutely. So take a peek and you'll find it. G. Ganbar, is Uranus pronounced Uranus or Uranus? Also, how do you avoid laughing at the sound of the word Uranus? I don't know. It's pronounced Uranus with the accent on the UR, basically. So definitely not Uranus, and Uranus is more correct, but not quite. There's no I there in Uranus. So Uranus, Uranus, Uranus. There's also several YouTube videos. One of the things you can do on that is, how do I pronounce Uranus? And there'll be several variants with different dialects or stresses on how to say the word. How to avoid laughing? I don't know. I guess I'm not 12 anymore. So I don't giggle at that, but I can understand why people will. I get it. But it's Uranus. And we will cover Uranus in this course when we get to the gas giants. Okay, we're at 10:23. That's the question. You can keep posting stuff on the discussion board, and I'll go back and look as we go through here. So what I wanted to do now was sort of do a little live module for you on time. So what I'm going to do is activate the screen sharing here, and I'm going to, let's see. Okay, let's go this way. So go over here, screen share. I will attempt to do just the time. Let's see how that does. Oh, that looks really excellent. It looks backwards to me. Nope, there we go. Okay, hopefully you can see that presentation. And I'm just going to walk through this. I need to make this fit the slides so I get as big as possible. Okay. So let's do it. Let's talk about time through the ages. So the passions of astronomy are no less profound because they are not noisy. This is a line out of John Steinbeck's novel, The Short Reign of Pippin IV. And it was the only political satire that Steinbeck wrote. It's short, it's a very short book. I encourage you to read it if you want to read something a little bit out of the norm of, you know, it was sort of the typical Steinbeck fare. And so it's the story of a commoner who has some long bloodline to King Charlemagne in France. The story takes place in France. And so at the current political currents of the day in France, the powers that be decide that he needs to be made king. So he is made king, and he doesn't like it, and he doesn't like it. One of the reasons he doesn't like it is that he cannot observe through his telescope anymore. So he's an amateur astronomer. And so he would often dress in disguise and get on his motor scooter, as is shown in the illustration here of this book, and take off and go doing observing. And so that's where this line comes from. The passions of astronomy are no less profound because they are not noisy. Noisy referring to the political climate in France at the time of the book. And so he has a short reign because the powers that be decide at some point, not too far after he's made king, that they no longer need him to be king. And so he is de-kinged, and he can go back to his enjoyment of astronomy as a commoner. It's a great read. Check it out. Time Through the Ages. And this is what we're going to talk about. I just happen to love this piece of artwork. I won't say this was done as a design project, but it might have been. So we have a clock, we have some gears, we got the grandfather clock thing going on the sun, and then we have some pointing to a constellation known as the Big Dipper in the current epoch. So time through the ages, let's talk about time. Okay. So time, you know, we start off in agricultural mode, and that agricultural dependence means knowing when to plant your crops, when to pick your crops, when is the first frost going to be, when is the last frost going to be, so that I know when to plant my seeds. And so as long as you're just going on what the sun is telling you the time is, both time through the day or time through the year, you're perfectly fine. No problem, just follow the sun. And it will let you know when you have to have a little bit of history. Okay, this is about when the last frost is going to be. But your clock is effectively set by the sun. So, but as societies grow more complex, they want fixed dates for things like festivals and tax paying. So the 4th of July, Halloween coming up, April 15th to pay your taxes, your birthday. So they want fixed dates, and that immediately introduces the problem of keeping the seasonal years, that is the time that the sun says it is, to the calendar, man-made calendar that you wish to impose. And you don't want to get those to get out of sync. In other words, you don't want to create a calendar such that you know, around when you're born, your birthday is in the summer, and then as you advance on in age, you suddenly find your birthday in the season of winter. Okay, that's what would happen if your clocks were unsynchronized. And you don't want that to happen. If you were born in early spring, you would like to keep your birthday in early spring for as long as you live and beyond. But keeping those clocks synchronized is hard. And we're going to see the implications of that as we go through. So just for the record, as we go along, for reference, the seasonal year is defined as the spring equinox, vernal equinox to the vernal equinox. So this is a particular point in the trajectory, and we just arbitrarily somewhat mark that as the 0 point. This is our 0 point. And so as we go around our elliptical orbit and we come back to the 0 point, that's going to define a year. So a year on Earth is about 365 days, 5 hours, 48 minutes, 46 seconds. There's a lot of precision there because we got better at marking time. Or 365.2422 days. And we'll use that 0.2422 days because it's less writing than all the hours, minutes, seconds as we go along. And the image here is, of course, The Persistence of Memory by Salvador Dali, 1931, and the melting clocks and keeping our man-made clocks in sync with the sun clock, the seasonal clock. So in the beginning, yearly calendars, so we'll start with the year. Yearly calendars were often based on a summer solstice to a summer solstice, or when a particular star first rises with the sun. And when a star rises with the sun, it's known as a heliacal rising. And the Egyptians used the star Sirius, which is the brightest star in the sky, and it rose with the sun in early July when the Nile was in flood. And with an economy, agricultural, again, going back to that, when that agricultural economy is based on Nile floods, this made the heliacal rising of Sirius the most important day of the year. And so at the time of the Egyptians, when Sirius rose with the sun, that was their January 1st, if you like. It was the first day of the year. And so the image here is showing a view from Alexandria, Egypt, at about 200 BC. At 5:40 a.m. And you can see the sun that's on the left. That's the mark there is the bright dot. The green line is the ecliptic. Right? So this is the plane in which the planets go in. And so you've got a couple of the planets there, Mercury, Venus, Uranus. And then you've got a number of common stars that people see, Betelgeuse, Rigel. Then you have Sirius, the brightest star in the night sky. It's rising in Canis Major. As it goes up. And so when it rises with the sun, that's when the first of the year was marked for the Egyptian calendar. So Sirius has many things along with us. So Sirius is the brightest star in the constellation Canis Major and is sometimes, as a result, called the dog star. Canis Major is a dog. And it is from the Egyptians' use of the heliacal rising of Sirius in early July that we get the phrase dog days of summer. So that phrase is actually quite old, going back at least to the Egyptians. The shot here is, the image here is some Uranographica, 1690, showing very artful constellations. Canis Major, Sirius, the dog star. So we go to the year. So that's how people define years for a while. And then year's kind of a long time. And so people wanted shorter ways to break the year up. And so how to mark time intervals within a year. And so the first marker that was used was that big orb that appears to go around the Earth, known as the moon. And in fact, that's what the root word of month is, month, moon. That's why they're related, because the month can be based on the moon. But there are two obstacles with using the moon to subdivide the year. The image here is the Aztec calendar stone, image taken about 1982 in Mexico City. I show it here because they used a lunar-based calendar to mark time within the year and beyond. So we got two problems here with using the moon to subdivide the year. The first obstacle is that the lunar month is variable. It's not fixed. It's somewhere between 29 and 30 days, which I suppose if that's the accuracy you care about, that might be okay. You're going to have to keep making corrections as you go along. And this variance of 29 to 30 days is due to the difference between not recognizing the difference between what is called the synodic period and the sidereal period. So the synodic period is something that's easy to observe. It's the time between, for example, 2 full moons, 2 quarter moons, 2 new moons. It's a visual thing. Full moon to full moon, for example, that would be the synodic period. And so if you use that, you find it's variable between 29 and 30 days. Then there's the sidereal period, which in some sense, it's got the word in it. It's the real period. It's the orbital period. And this is the time between identical star, Earth, and object alignments. This is the real period. This is the period that you put in Kepler's third law, that you put in Newton's form of Kepler's third law. It's the physical period, but it's a lot harder to observe. It's not as blatantly obvious as full moon to full moon. So let's talk about let's show why that is different, those two. So I'm going to start with everything all very nicely aligned here. So I'm going to have the sun on the left. I have the Earth orbiting the sun. I have the moon in purple orbiting the Earth, more correctly, the center of mass of the Earth, of the Earth-Moon system. And then I have a distant star. And right now I've got them all aligned, so everybody's in line, and I'm going to start my clock. Okay, so go. So Earth will progress around its orbit, and the moon will do its thing. And so by the time that you get back to the same alignment between the Earth and the moon and a distant star, let's say Sirius, that is the real period. That is the sidereal period. It's 27.322 days. Okay, but the moon is not full, right? So in our original alignment, the moon is full because we have the sun, Earth, and moon alignment in that order, and so that gives a full moon. And so by the time Earth orbits around, I have to go a little bit extra distance to get around to the full moon again, primarily because the Earth has moved along in its orbit. Okay, so I got two moving circles, if you like, and it takes a little bit of extra time for those markers on those circles to line up again. Okay, and so the time that it takes to reach the full moon is variable, 29 to 30 days. It's variable because Earth's orbit is not perfectly circular. It's very close, but it's not perfect. And so when the Earth is closer to the sun, it moves faster. When the Earth is farther away from the sun, it moves a little slower. And so that's one part of variance in why the period between full moons varies. So that's the difference between the synodic and a sidereal period. Okay. And the second obstacle to using the moon as a marker for the month is that the year cannot be divided, let's say, by the average lunar month of 29.5. 12 lunar months is too short by about 11 days, and if I go with 13 lunar months, it's too long by about 19 days. And so if you use a lunar calendar, you will slowly get out of step with the calendar that the sun says, the seasonal calendar. So that eventually, if you wait long enough, if you don't have those two aligned, then the hottest time of the year would eventually occur in what you're calling the winter months, because your clocks have gotten out of sync. Nevertheless, the moon is such a convenient marker for periods within the year that cultures went ahead and did it anyway. And many cultures got around this conflict of it doesn't fit evenly and it's variable by inserting an extra 13 months every couple of years in order to resynchronize the seasonal and calendar years. So seasonal is the seasonal calendar is what the sun says, and then our calendar years is the system that we're imposing. And so you would do it sort of randomly as it goes through, and you would get that. Okay, and so the moon has also been with us culturally for quite a while. And so it was accepted practice in Babylon about 4,000 years ago that for a month, full moon to full moon, after a wedding, that the bride's father would supply his son-in-law with all the mead he could drink. And so mead is a honey beer, and since the calendar of the Babylonians was lunar-based, this period of time is called the honey month, or morphed into what we call today as the honeymoon. So that's the origin of our term honeymoon. And the moon inspires many other phrases: lunatic, luna, la luna, lunatic, a blue moon, a wet moon, a harvest moon, many moons with names for stuff. But I just find the honeymoon one in particular fascinating because it goes back in time so long. So the Egyptians took a more radical approach. So this is the first attempt at imposing rules for the calendar year to keep in touch with the seasonal year. Instead of just doing things randomly when it felt good, when it looked like it was a little too far out of sync, okay, let's do something a little more orderly. And so the Egyptians were the first to give up on using the moon to mark the month, and they took a more radical approach. So they are the ones that divided the year into 12 months. There's our 12, right? 12 months, 12 hours a day, 12 hours a night, all from the Egyptians, Babylonians. They divided the year into 12 months of 30 days each. Okay, so that's easy enough. So that gives 360 days. But they knew that 360 days was not a good approximation to the year. And so at the end of every year, they added 5 more days for an approximation of 365. But even the Egyptians knew 365 was not the best of approximations. And so extra days were inserted randomly in order to keep the seasonal and calendar years synchronized. And so that was the system of the Egyptians trying to impose some order. So this lasted for a while. The Romans had initially had quite a surprisingly messy calendar. A month was 10 days long. The first of the year was in March, the Ides of March. And the empire was also big, and so different parts of the empire were inserting days at random in order to keep their local seasonal calendar in touch with the man-made calendar. Quite a mess, but nevertheless still with us. The months, September, October, November, December, are with us from being in the Roman calendar what were the 7th, 8th, 9th, and 10th months in the Roman calendars. So if you speak Spanish or you speak a language like that and you just count to 10, you will pick up 7, 8, 9, 10, right? 7, 8, 9, 10, even though these days they are not the 7th, 8th, 9th, and 10th in the modern calendar year. And we'll get to why that is in a minute. But nevertheless, the Roman calendar is still with us in the names for September, October, November, December. So with this sort of randomness of corrections and length of time in the Roman Empire, it was Julius Caesar who imposed some order on the calendar. And so a year before his death, the Ides of March, Julius Caesar instituted a new calendar across the Roman Empire. So local entities couldn't have their own calendar anymore. We have 12 almost equal months. This is where we start jittering how many days are in a month. March is still the first, March being the first. And they were almost equal, and they totaled 365 days. And now he puts in the first major correction, where every 4th year, or leap year, an extra day was added at the end of the year. And this gave an average year of 365.25 days. Pretty good, pretty good. Closer. And so this is known as the Julian calendar. And of course, it's still with us. We still have leap years every 4 years in order to try and get a better approximation to the seasonal year. Now Julius liked his system so much that well, you know, money and power kind of go together, even in the time of the Romans, and so Julius, who took a month, he liked his calendar so much, he took a month for himself. July, Julius, July, okay? And his powerful, rich friends were known as the Juno family. And he decided to honor his benefactors by naming a month in his revamped new calendar after them. And so the Juno family got the month June, June and July for Juno family and Julius Caesar. So now the pattern was set. So now every subsequent ruler of Rome had to take a name of the calendar for himself. Fortunately, most of those did not stick. The only one that stuck was Julius's grandson, Augustus Caesar, and it is from Augustus Caesar that we get the month August. So June, July, and August are from the days of Julius and Augustus Caesar and their power structure. So that's how we get June, July, August, September, October, November, December. All those names coming from the Roman calendar. So 365.25 is close, but it's not 365.2422. And so the Julian calendar is about 11 minutes too long, or about 1 day after 130 years, or about a week after 1,000 years. And so, okay, that's sort of, okay, we're just going to punt on the problem and not worry about it. But guess what? 1,000 years did go by, more than 1,000 years, until we get to about the year 1582, where the seasonal and calendar years were about 10 days out of sync. And this was noticeable to people. And so there was a call to resync the calendars. So at this time, the Catholic Church is the power structure in the world. And so Pope Gregory decides he has to do something radical in order to bring the synchronization back. And so he introduces the system that is still with us today and is called the Gregorian calendar. So I want you to take a look at this calendar, 1582 in October, and you'll notice something about that calendar. October 1, 2, 3, 4, 15. You just lopped 10 days out of the calendar. You have to do that if you want to resync. So you got to reset the 0 point clock. And of course, this caused social mayhem. Do I still get paid for those days? What if my birthday was October 6th? I don't get a birthday anymore. Do I have to pay taxes on those days? Social chaos. But it worked out, but not without consternation. And so things got somewhat straightened out, and we carried on with a new 0 point. So we're going to now resync the calendars. So, okay, now things are aligned. And this is where Pope Gregory, not wanting to keep the 0 point of the pagan Romans, this is where we get January 1 was made the beginning of the year. That's still with us. And just like the Romans, Julius Caesar's calendar, every 4 years we have an extra day is added to February. So that's fine. He hasn't really done too much. All Pope Gregory has done is, okay, resync the calendars, and he's still using Julius's leap year mode to get a better approximation to the length of the year. But now he adds a new twist, a new correction term. And that new correction term is that century years that are divisible by 400 are also leap years. And so 1700, 1800, and 1900 are not leap years because they're not evenly divisible by 400. But the years 1600 and Y2K or 2000 are leap years. So we just went through Y2K 18 years or so ago. And so if your century year happens to be divisible by 400, that is also a leap year. So this is a better approximation. And so the Gregorian system is 38 seconds too short, or about 1 day in 2,200 years. So this synchronization problem has been with us thousands of years now. And what are we going to do? Are we going to wait 2,200 years again and go through the same social cultural problems that it takes to resynchronize the calendars again? Or worse, wait till 10,000 years go by and the calendars are seriously out of sync again and you got to do some major surgery? No, we don't do that anymore. Okay, so what we do these days is 1 second is added to the calendar clock when it is necessary at midnight on June 30th or December 31st, whenever the difference between the seasonal and calendar year reaches 1 second. So we add 1 second whenever it is necessary. It's not always necessary. You're not required to add a second on June 30th or December 31st. But you can if those the time difference between the seasonal and calendar clocks differ. And so you may have read somewhere as you've gone through where, oh, there's going to be an extra second in the year. And that's done on June 30th or December 1st. That's fine. This system was all pretty much set up before serious advent of computers. And so even that 1 second difference that is added randomly, basically, according to what Earth's rotation is doing, causes problems with computer systems and stock markets. In an electronic-driven world, 1 second is a big deal. And how to plan for that 1 second is a big deal. So there's lots of proposals on what to do now with the refinement of a single second. So there are 2 entities that keep track of time for us. One is the calendar clock. That's the time we want. This is our self-imposed man-made system. Is maintained by the Bureau of International Des Points. I'm going to butcher my French there, so I'm not even going to say it. Using a worldwide network of atomic clocks. And so the atomic clocks are accurate to about 10 to the minus 12 picosecond. And this is the time we wish to impose. And so the seasonal clock is what actually sets that, right, is Earth's rotation. And Earth's rotation changes. The Earth is not it deforms a little bit, it slows down. Lots of things can change the rotation rate of the Earth by small amounts. And so there is an entity, U.S. Naval Service, in this lovely building shown here on the right. It looks like, I don't know what. It's pretty ugly. Cement building, bars on the doors. You can see the telescope dome back there. And they keep track of the Earth's rotation, which is a seasonal clock. And so keeping that calendar clock and seasonal clock together is the name of the game, and it's still with us. We're better. We only do adjustments twice a year, but even that is disruptive in today's modern electronic world. Okay, so we covered the origin of the year up to the modern time, subdivisions within the year, the month, somewhat lunar based these days. But how about days of the week? Why are there 7 days of the week? There are 7 days of the week because when people looked up at the night sky in antiquity, there were only 7 objects that moved. And so they were special. Everything else appeared not to move at all. They were like a sticky dot on the celestial sphere. And so the 7 that moved, they were special enough that they all got their own name. And they were associated with various deities in the celestial sky. And so the only thing that changed on the night sky were the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. These were the objects you could see with your naked eye in antiquity, and they were special. And so our names for the 7 days of the week come from the North Celtics, where we have Sunday, that should be obvious, Moon Day, Monday, obvious, Tuesday, Mars, Tew in Celtic. Then we have Woden Day, Wednesday, Mercury Day, Thor Day, Thursday, Jupiter. And then the only female in the group, Freya Day, Friday, Venus. And then Saturn Day, Saturday, and that one's a little more obvious. So even the names of the days of our weeks are named after, have an astronomical origin to them in keeping time. So astronomy has been central to our concepts of time and how we subdivide time, what we call time, how we mark time. Now, what time zones? Where time zones come from? Here's a time zone map, current time zone, relatively current time zone map of the world. And so where time zones come from? Well, before time zones happened, every region set their clocks according to the local astronomy conditions. So noon in Flagstaff was not necessarily noon in Phoenix, which is not necessarily noon in Tucson, Arizona. That was fine. That's the right thing to do, is to set your clock by your local conditions. But it causes a problem when you start wanting to have large-scale transportation systems. So, for example, the trains were the first ones. So when you publish a schedule, whose clock are you talking about? Or when you say depart and arrive, are you referring to the departure city where you left, or the arrival city, or is it one in one and one in the other? Oh, what a mess. And so it was transportation systems, in particular the trains, the train companies that set up, okay, we're going to go with 4 time zones in the U.S. And so these were introduced by the railroads in 1883 in order basically to standardize the schedules. And then in 1918, it worked so well, and of course by that time we had more and more transportation systems coming on, that the Congress, U.S. Congress, made the time zones official under federal law. But you were still given the, that's another one, we'll leave that one alone. And so that's how we got that. And then that system worked well enough, and as transportation systems spread beyond the U.S. to the rest of the world, airplanes in particular, so air transportation, it was the forerunner of the United Nations in the 1930s, that instituted time zones across the world. So we have 24 time zones because they're 24 hours roughly in a day. And allowance is made for geopolitical realities. That's why you don't see in this time zone map, there are very few time zones that are perfectly straight with no jig-jags. So the time zones are allowed to jig-jag. Even in the US, they're not straight lines, right? They jig-jag according to convenience. And so you do the same thing in the world. You do it for convenience on various geopolitical, economic realities. So that's how we got time zones. Okay. And so I will just end on this interlude on astronomy and clocks and time. And so that's a little bit about years and months and weeks and days and how we got to the system that we have right now. Okay. Thanks. Okay. So I'm going to not screen share. Where is my not screen share button? Okay. Okay, stop my screen sharing. There we go. Screen sharing done. Okay, so this can go away. Okay, where are we at? We are at 10:58, so we have 2 minutes. I will do a quick check of the questions. Discussion board, topics. And I see no new questions in our YouTube Live 1 session. Okay, far out. Thank you very much for listening, for watching. And we will do another one of these. Instead of at 0500 UTC, we'll do it at 1700 UTC in order to pick up another half of the globe, different times. So locally, this is 10 p.m., 11 p.m. Arizona. Next time will be 10 a.m., 11 a.m. Arizona time. Okay, I want to thank you very much. Ask your questions on the discussion board for either the quantitative or qualitative questions as we go through, and I look forward to interacting with you on the discussion boards. See you in a few weeks. Bye-bye.